All right, in the last video, we talked about something called heat of formation and the heat of formation equation. It's based on something called Hess's Law. So a little background on Hess's Law. Not all reactions can have a delta H determined for them as written. So what that means is that if I have generic equation A plus B yields C plus D, it may not be possible to turn A plus B directly into C plus D. It might be a two-step process where I have to get E, then add F to E, and then make C plus D. So, but if I want just the delta H for that overall reaction, I can use something called Hess's Law. Okay. Hess's Law is based on the fact that enthalpy change is a state function, which means the delta H for a reaction is independent of how you change the reactants into products. Remember, we're looking at the difference between products and reactants, and we're ignoring the hill on the energy diagrams. Okay. So the enthalpy change for a reaction is the same whether the reaction is carried out in 1 step, 2 steps, 5 steps, or 10 steps, as long as the initial reactants turn into those final products. And you can see here the statement of Hess's Law, but what does that really mean? Let's take a look at this picture. Okay. Here are my reactants. I'm going to burn some methane. So there's CH4 plus O2. I burn it and turn it into CO2 gas plus H2O liquid. Okay. And 890 kilojoules of energy is released when those reactants turn into products. But when you actually burn methane, it's really hot. So a lot of times, you end up with H2O gas instead. The delta H for that reaction is different. It's only changing these reactants into CO2 plus H2O gas. The delta H is negative 802 kilojoules. Then if I take that H2O gas and condense it, an additional 88 kilojoules of energy is released, and I get H2O liquid. So when I look at this diagram, it's easy to see that delta H1 is equal to delta H2 plus delta H3. That is Hess's Law. So let's take a look at a Hess's Law problem. Okay, we're going to calculate the delta H for this reaction based on these 3 reactions that are given. So what you want to do is just kind of break it apart. Okay, I want H3BO3 as a reactant. This is the equation that has H3BO3 as a reactant. So I'm going to rewrite that equation as written. Okay, now you'll notice this is 1 H3BO4, that's 2. So if I want 2, I simply multiply all the coefficients by 2, and this reaction right here, so now I have 2, 2, and 2, and then the delta H for this reaction is also going to get multiplied by 2. So there's where my H3BO4 is going to come from as a reactant. Then you'll notice there are 2 products, B2O3 and H2O. Since H2O is in every equation in here, I'm going to ignore H2O for right now. I'm going to focus on B2O3 because B2O3 is only in this equation. Now, in my overall reaction, B2O3 is a product. It's a product in the reaction I'm given, so I'm going to leave that reaction as written. Now, what you'll notice is that there are 2 B2O3s here, but I only want 1 in my overall reaction. So I'm going to multiply everything by 1/2. So 1/2 of 1 is 1/2. 1/2 of 2 is 1, so that gets rid of that 2. And I have a half over here, which means that I need to take this delta H and multiply it by 1/2. Okay, now let's look at the third reaction, the one I haven't used yet. Okay, now you'll notice I have H2B4O7, and I also have this HbO2. Okay, I need to get rid of both of these things. So you'll notice H2B407 is a reactant. In this reaction, it's a reactant here. If I want them to cancel, I can flip this reaction. So I'm going to write this in reverse. And then we'll take a look at coefficients. So I have 4HBO2 yields H2B407 plus H2O. Now, the other problem is, oops, that should be HBO2. The other problem is there's only 2 HBO2s I need to get rid of. There's 4 here, so that would still leave me with HBO2s. If I, again, multiply everything by 2, all my coefficients, so I'm going to multiply that by 1/2, that gives me 2 of those. That gives me 1/2 of those, and 1/2 of those. Now, when I look at the delta H, the first thing is I have to multiply it by 1/2, because I multiplied the coefficients by 1/2. The second thing is I flipped this reaction. So this reaction as written is exothermic, negative delta H, which means if I flip the reaction, it becomes endothermic. So now if I look at what I have, 2 HBO2s here, 2 HBO2s there, they cancel out. 1/2 H2BO7 there, 1/2 H2BO7 there, they cancel out. What I have left is 2 H3BO3 yields B2O3, because there's just one of them, and you'll notice there are 3 H2Os. So now I get the overall reaction, my target reaction. And to get the delta H, I have to add up those 3. If I add up those 3, I get